What lies beyond the boundaries of everything we know? This question has puzzled humanity for millennia, driving scientific inquiry to the edge of comprehension. From the mind-bending concept of a cyclic universe to the possibility of extra dimensions predicted by string theory, our understanding of reality continues to evolve. We stand on the precipice of revolutionary ideas, dark energy shaping cosmic destiny, holographic principles challenging our perception of space, and quantum fluctuations birthing new universes. As we explore these frontiers, we confront big questions about our place in existence. Are we part of a massive multiverse, or could our reality be a simulation?
The observable universe encompasses all the matter and energy we can detect from Earth, stretching out in every direction to the farthest limits of our view. This cosmic horizon is not a physical boundary, but rather the extent to which light has had time to reach us since the birth of the universe. Approximately 13.8 billion years ago, light, though incredibly fast, is not instantaneous. It takes time for the radiance of distant stars and galaxies to traverse the vast cosmic distances and arrive at our telescopes. The most distant objects we can observe are those whose light has been traveling toward us for nearly the entire age of the universe. This means that when we peer into the depths of space, we are also looking back in time. The light from the edge of the observable universe began its journey when the cosmos was in its infancy, just a few 100,000 years old. As we look closer to home, we see celestial objects as they appeared more recently.
The observable universe is constantly expanding as light from ever more distant regions finally reaches Earth. However, due to the expansion of space itself, there are regions of the universe that we will never be able to see, no matter how long we wait. These areas lie beyond our cosmic horizon, forever out of reach, making the observable universe a finite glimpse of a potentially infinite cosmic expanse. The observable universe stretches an immense 93 billion light-years in diameter. This vast expanse represents the farthest distance we can see in any direction from Earth, limited by the speed of light and the age of the universe. Light from the most distant objects has taken nearly 14 billion years to reach us, traveling since shortly after the Big Bang. However, due to the expansion of space itself during this journey, those objects are now much farther away than 14 billion light-years.
This cosmic horizon continues to grow as time passes, with more distant regions becoming visible to us. Yet there likely exists much more universe beyond what we can observe, potentially stretching to infinity. Our view is fundamentally limited by the finite age of the universe and the constant speed of light. The sheer scale of the observable universe challenges human comprehension, encompassing countless galaxies, each home to billions of stars and planets. It serves as a humbling reminder of our place within the cosmic tapestry.
The observable universe has boundaries, not because space itself ends, but due to the finite speed of light and the age of the universe. Light from the farthest reaches of space has been traveling towards us for billions of years. Yet there are regions so distant that their light hasn't had time to reach us since the Big Bang. This cosmic horizon, known as the observable universe, extends approximately 93 billion light-years in diameter. Beyond this limit, we cannot see or detect anything, as the light from those regions has not yet had sufficient time to reach Earth. It's important to note that this boundary is not static. It continues to expand as time passes and more distant light reaches us.
The expansion of the universe further complicates our observations. As the universe expands, light from distant objects is stretched, shifting towards longer wavelength in a phenomenon called redshift. For the most distant objects, this redshift is so extreme that their light becomes undetectable to our instruments. Additionally, the early universe was opaque for its first 380,000 years,
filled with a dense fog of hydrogen plasma. Only after this period did the universe become transparent, allowing light to travel freely. This event, known as recombination, creates another barrier to our observations, as we cannot directly see anything that occurred before this time using electromagnetic radiation.
The cosmic horizon marks the boundary of our observable universe, defining the farthest reaches of space from which light has had time to reach Earth since the beginning of the universe. This horizon is not a physical barrier but rather a limit imposed by the finite speed of light and the age of the universe. Light travels at a constant speed, taking time to cross vast cosmic distances. The farther we look into space, the further back in time we see. The cosmic horizon represents the most distant light that has had enough time to reach us, about 13.8 billion years. The observable universe is everything within this cosmic horizon, a spherical volume centered on Earth, with a radius of about 46 billion light-years. This size accounts for the expansion of space itself, which allows the observable universe to be larger than one might expect based solely on the age of the universe and the speed of light. Beyond the cosmic horizon lies the unobservable universe, regions so distant that their light has not yet had time to reach us. As time passes, more of the universe becomes observable, gradually pushing our cosmic horizon outward and expanding our view of the cosmos. Our understanding of the universe's size has undergone a dramatic transformation throughout history. Ancient civilizations believed the Earth was the center of a relatively small cosmos, with the stars as fixed points on a celestial sphere. This geocentric model persisted for centuries, limiting our concept of the universe's true scale. The scientific revolution brought significant changes. In the 16th century, Copernicus proposed a heliocentric model, placing the Sun at the center of our solar system. This shift expanded our cosmic perspective, but the universe was still thought to be much smaller than we know it to be today. A major leap came in the early 20th century, when Edwin Hubble proved that the Milky Way was not the entire universe but just one of many galaxies. His observations of distant nebulae revealed a vast cosmos beyond our own galaxy, expanding our understanding of the universe's size by orders of magnitude.
Modern astronomy and space exploration have further expanded our cosmic horizons. We now know the observable universe spans approximately 93 billion light-years in diameter, containing hundreds of billions of galaxies, each home to hundreds of billions of stars. This immense scale, unimaginable to our ancestors, continues to grow as our instruments and knowledge improve, revealing an ever-expanding cosmos that challenges our comprehension.
Astronomers employ a diverse array of sophisticated tools and technologies to unravel the mysteries of the observable universe. At the forefront are powerful optical telescopes, both ground-based and spaceborne, that capture visible light from distant celestial objects. These include behemoths like the 30-meter telescope and the orbiting Hubble Space Telescope, which have revolutionized our understanding of cosmic structures. Beyond visible light, astronomers harness the entire electromagnetic spectrum. Radio telescopes, such as the Very Large Array in New Mexico, detect radio waves emitted by stars, galaxies, and other cosmic phenomena. X-ray and gamma-ray observatories, like the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope, unveil high-energy processes in the universe, from black holes to supernovae. Infrared telescopes, exemplified by the James Webb Space Telescope, peer through cosmic dust to reveal stellar nurseries and distant galaxies. Ultraviolet telescopes uncover hot young stars and active galactic nuclei. These multi-wavelength observations provide a comprehensive view of celestial objects and events. Complementing these traditional tools, astronomers now utilize cutting-edge technologies like adaptive optics to counteract atmospheric distortion, interferometry, to combine multiple telescopes into virtual giant instruments and advanced computer simulations to model cosmic processes. Gravitational wave detectors like LIGO have opened an entirely new window into the universe, allowing us to hear cosmic collisions and explore the nature of space-time itself. The expansion of the universe fundamentally shapes our view of distant cosmic objects. As space itself stretches, light from faraway galaxies and stars must travel through an ever-expanding medium. This expansion causes the light to be stretched, shifting its wavelength towards the red end of the spectrum. We call this phenomenon redshift, and it becomes more pronounced the farther away an object is from us. This cosmic expansion presents both challenges and opportunities for astronomers. On one hand, it limits our ability to see the most distant objects clearly, as their light becomes increasingly redshifted and fainter. Some objects are so far away that their light has been stretched beyond the visible spectrum entirely, requiring specialized infrared telescopes to detect them. However, the expansion also provides a valuable tool for measuring cosmic distances. By analyzing the degree of redshift in an object's light, scientists can calculate how far away it is and how fast it's moving away from us. This information is crucial for mapping the structure and history of the universe.
The expansion of the universe also means that there's a limit to how far we can see, known as the observable universe. Beyond this cosmic horizon, light from more distant objects hasn't had enough time to reach us since the beginning of the universe. As the universe continues to expand, some galaxies will eventually move beyond our cosmic horizon, becoming forever invisible to us.
The cosmic microwave background is a crucial piece of evidence that helps us understand the early universe and its current limits. This faint glow of radiation permeates all of space and represents the oldest light in the universe, dating back to about 380,000 years after the Big Bang. When we observe the cosmic microwave background, we are essentially looking at the edge of the observable universe. It acts as a cosmic horizon beyond which we cannot see directly. This radiation provides a snapshot of the universe when it first became transparent to light, marking the point where the universe cooled enough for atoms to form. The uniformity of the cosmic microwave background across the sky supports the idea of cosmic inflation, a period of rapid expansion in the early universe. This expansion helps explain why the universe appears flat and homogeneous on large scales, addressing fundamental questions about the universe's structure. By studying tiny fluctuations in the cosmic microwave background, scientists can infer information about the composition and evolution of the universe. These fluctuations serve as seeds for the cosmic structures we see today, from galaxies to galaxy clusters, providing insight into how the universe transformed from a nearly uniform state to the complex cosmos we observe now. The multiverse theory proposes that our universe is not alone, but part of a vast collection of universes existing simultaneously. This concept suggests that beyond the boundaries of our observable cosmos lie countless other universes, each potentially with its own unique laws of physics, fundamental constants, and possibly even forms of life. According to this theory, these universes might be separated by higher dimensions or exist in parallel, like sheets of paper stacked together. Some versions of the multiverse theory stem from the principles of quantum mechanics, where every possible outcome of a quantum event could create a new universe. Others arise from string theory and the idea of eternal inflation, where new universes continually bubble into existence. The multiverse concept challenges our understanding of reality and raises profound questions about the nature of existence. If true, it would mean that everything we know, from the laws of physics to the very fabric of space and time, might only apply to our particular universe. Other universes could have entirely different properties, from subtle variations to radically alien configurations. While the multiverse theory is fascinating, it remains highly speculative and currently impossible to test directly. Scientists continue to explore its implications and search for indirect evidence that might support or refute this mind-bending idea about the structure of reality.
The multiverse theory proposes the existence of multiple universes beyond our own, challenging the traditional single universe model. While the single universe concept suggests that our observable cosmos is all that exists, the multiverse theory opens up a vast array of possibilities. In the multiverse scenario, our universe is just one of many, potentially infinite universes existing simultaneously. These universes might have different physical laws, constants, or initial conditions, leading to diverse realities. Some theories suggest these universes could be separated by higher dimensions or exist in parallel.
The single universe model, by contrast, posits that our observable universe is unique and self-contained. It assumes that the physical laws and constants we observe are universal and unchanging throughout all of space and time. One key difference lies in how these models address fine-tuning questions. The single universe model struggles to explain why our universe seems perfectly tuned for life, while the multiverse theory suggests that in a vast array of universes, some will inevitably have conditions suitable for life to emerge. This shift in perspective has profound implications for our understanding of cosmic origins and the nature of reality itself.
The concept of a multiverse is supported by several scientific theories and principles. Quantum mechanics, a fundamental theory in physics, suggests the existence of multiple parallel universes through its many worlds interpretation. This interpretation proposes that every possible outcome of a quantum event occurs in a separate universe, leading to an infinite number of parallel realities.
String theory, another prominent framework in theoretical physics, also lends support to the multiverse idea. It postulates that our universe is just one of many universes, each with its own set of physical laws and constants. These universes are often described as existing in higher dimensions beyond the four we can directly observe.
Inflationary theory, which explains the rapid expansion of the early universe, provides another avenue for multiverse speculation. Some versions of this theory suggest that inflation continues eternally in some regions of space, constantly creating new universes in a process called eternal inflation.
The anthropic principle also plays a role in multiverse theories. It addresses the seemingly fine-tuned nature of our universe, suggesting that out of countless universes with different properties, we naturally find ourselves in one capable of supporting life. This principle helps explain why our universe appears so well suited for our existence, without resorting to supernatural explanations.
Scientists have proposed several different types of multiverses, each with its own unique characteristics and implications for our understanding of reality. The concept of multiple universes has gained traction in theoretical physics and cosmology over recent decades.
One widely discussed type is the many-worlds interpretation of quantum mechanics, which suggests that every possible outcome of a quantum event occurs in a separate universe. This leads to an infinite number of parallel universes branching off from each quantum decision point.
Another proposal is the inflationary multiverse, based on the theory of cosmic inflation. This model suggests that our universe is just one of many bubble universes that formed during the rapid expansion of space in the early moments after the Big Bang. Each of these bubbles could have different physical laws and constants.
String theory, a candidate for a unified theory of physics, has also given rise to the idea of a multiverse. The landscape of string theory allows for an enormous number of possible universes, each with its own set of physical laws. Some scientists estimate this number could be as high as 10 to the power of 500 distinct universes.
The bubble universe concept is a fascinating aspect of multiverse theory that proposes our universe is just one of many universes existing simultaneously. In this model, each universe is likened to a bubble floating in a vast cosmic sea. These bubbles can form, expand, and potentially even collide with one another.
According to this idea, during the earliest moments of cosmic creation, the fabric of space-time underwent a period of rapid expansion known as inflation. This expansion was driven by a hypothetical field called the inflation field. As this field decayed, it released enormous amounts of energy, giving birth to our observable universe. However, the bubble universe concept suggests that this process of inflation and decay might not have happened uniformly everywhere. Instead, different regions of space could have experienced varying rates of inflation, leading to the formation of separate bubble universes. Each of these bubbles would have its own laws of physics, fundamental constants, and potentially even different dimensions. This concept opens up mind-boggling possibilities. There could be an infinite number of these bubble universes, each with its own unique characteristics. Some might be similar to our own, while others could be wildly different, perhaps incapable of supporting any form of life as we know it. The bubble universe idea offers a potential explanation for the apparent fine-tuning of our universe, suggesting that we simply happen to exist in a bubble with the right conditions for our form of life to emerge. Quantum mechanics and the concept of multiple universes are intricately linked through the many worlds interpretation. This theory, proposed by physicist Hugh Everett, suggests that every quantum event creates a branching of reality into different universes. When we observe quantum particles, they exist in a state of superposition, meaning they can be in multiple states simultaneously. However, upon measurement, we only see one specific outcome. The many worlds interpretation posits that all possible outcomes actually occur, each in a separate universe.
This mind-bending idea implies that our universe is just one of countless others, each representing a different outcome of quantum events. Every decision we make, every coin flip, and every quantum fluctuation could spawn new universes. These parallel worlds would be nearly identical to ours, differing only in the outcome of that specific quantum event.
While this interpretation remains controversial, it offers a fascinating perspective on the nature of reality and our place within it. It suggests that the universe we experience is just one thread in an infinitely complex tapestry of possibilities, all stemming from the strange behavior of quantum particles. The many worlds interpretation is a fascinating concept in quantum physics that challenges our understanding of reality. Proposed by physicist Hugh Everett in the 1950s, this theory suggests that every time a quantum event occurs, the universe splits into multiple parallel realities. In this view, all possible outcomes of quantum measurements actually happen, each in a separate universe. For example, when we measure the spin of an electron, instead of it randomly choosing to be either up or down, both outcomes occur simultaneously in different universes. This means that for every decision we make, every coin we flip, and every quantum event that takes place, a new universe branches off. The implications of this interpretation are mind-boggling. It suggests that there are countless versions of ourselves living out different lives based on different choices and outcomes. These parallel universes are thought to be entirely separate and unable to interact with each other, which is why we only experience one reality. While the many worlds interpretation offers a solution to some paradoxes in quantum mechanics, it remains highly controversial. Many scientists find it difficult to accept the idea of an ever-multiplying number of universes. However, it continues to intrigue physicists and philosophers alike. pushing the boundaries of our understanding of quantum reality and the nature of existence itself. The concept of parallel universes, also known as the multiverse theory, suggests that our universe might be one of many existing simultaneously. While this idea remains theoretical, scientists have proposed several ways these universes could potentially interact. One possibility is through quantum entanglement. This phenomenon, observed in our own universe, allows particles to be connected regardless of distance. Some physicists speculate that quantum entanglement might extend beyond our universe, creating subtle links between parallel realities. Another theoretical interaction involves cosmic collisions. Some models propose that universes could exist as membranes or branes floating in a higher dimensional space. If these branes collide, it could cause ripples in both universes, potentially observable as gravitational waves or unusual cosmic events. Wormholes offer another hypothetical means of interaction. These theoretical tunnels through space-time might connect not just distant parts of our universe, but also bridge separate universes. However, the existence of wormholes remains unproven, and their stability and traversability are subjects of ongoing debate in the scientific community. While the concept of a multiverse is intriguing, direct observational evidence remains elusive. However, several indirect lines of evidence and theoretical considerations lend support to the idea. One potential piece of evidence comes from cosmic microwave background radiation. Some scientists argue that certain anomalies in this ancient light could be explained by the influence of other universes. These include unexpected cold spots and alignments in the radiation pattern that are difficult to account for in a single universe model. Quantum mechanics also provides theoretical backing for the multiverse concept. The many worlds interpretation suggests that every quantum event creates multiple realities, potentially giving rise to countless parallel universes. While we cannot directly observe these other worlds, the mathematics underlying quantum theory is consistent with their existence. String theory, a candidate for a unified theory of physics, often predicts the existence of multiple universes as a natural consequence of its framework. The theory requires extra dimensions, and some versions suggest that our universe might be just one of many branes floating in a higher dimensional space. Although string theory remains unproven, its mathematical consistency adds weight to multiverse ideas. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny vibrating strings of energy. These strings, which are incredibly small, about 100 billion times smaller than atomic nucleus, are thought to vibrate in different ways, giving rise to all the particles and forces we observe in nature. According to string theory, our universe might have as many as 10 or 11 dimensions, most of which are curled up and invisible to us. This concept challenges our everyday understanding of reality, which only perceives 3 spatial dimensions and 1 dimension of time. The extra dimensions proposed by string theory could explain why gravity appears so much weaker than the other fundamental forces of nature. String theory attempts to unify all the known forces in the universe, including gravity, into a single coherent framework. This makes it a promising candidate for the long-sought theory of everything, which would explain all physical phenomena in the universe, from the smallest subatomic particles to the largest cosmic structures. However, string theory remains highly speculative and unproven. Scientists have yet to find experimental evidence to support its predictions, and some critics argue that it might be untestable. Despite these challenges, String theory continues to fascinate physicists and cosmologists as they seek to understand the deepest mysteries of our universe.
String theory, one of the most intriguing and complex ideas in modern physics, proposes a universe with far more dimensions than we can perceive. While our everyday experience is limited to 3 spatial dimensions and 1 dimension of time, string theory suggests that reality might encompass 10 or 11 dimensions in total. These extra dimensions are thought to be tightly curled up and incredibly small, existing at scales far tinier than even subatomic particles.
The idea is that these hidden dimensions could explain many of the mysteries that continue to puzzle physicists, such as the nature of dark matter and the unification of fundamental forces. The exact number of dimensions proposed by string theory has evolved over time. Initially, the theory required 26 dimensions, which was later refined to 10. An extension of string theory, known as M-theory, proposes 11 dimensions.
These additional dimensions are not just mathematical constructs, but are believed to have real physical significance, potentially shaping the very fabric of our universe. Understanding these extra dimensions is crucial for string theory's attempt to reconcile quantum mechanics and general relativity, 2 pillars of modern physics that have long resisted unification. While we cannot directly observe or interact with these extra dimensions, their existence could have profound implications for our understanding of the cosmos and the fundamental nature of reality. In string theory, brains are fundamental objects that exist in multiple dimensions. The term brain is short for membrane, though these structures can have various dimensions. Brains can be thought of as sheets or surfaces that extend through space and time, serving as the foundation for our universe and potentially others. String theory proposes that our universe might be a 3-dimensional brain floating in a higher dimensional space. This larger space, often called the bulk, could contain other brains, each representing a distinct universe. These universes might be parallel to ours, separated by extra dimensions we cannot directly observe or interact with. The concept of brains offers a fascinating explanation for the multiverse theory. It suggests that what we perceive as our entire cosmos might be just one of many universes, each existing on its own brain. These universes could have different physical laws, constants, or even different numbers of dimensions.
Interactions between brains could potentially explain some cosmic phenomena. For instance, some physicists have proposed that the Big Bang might have been caused by a collision between 2 brains. This idea opens up new avenues for understanding the origin and evolution of our universe, as well as the possibility of other universes beyond our own.
Extra dimensions could be hidden from our everyday experience in several intriguing ways. One possibility is that these dimensions are incredibly small, curled up into tight loops that are far too tiny for us to detect with our current technology. Imagine a tightrope walker on a wire. From a distance, the wire appears to be a 1-dimensional line, but up close, an ant could walk around the circumference of the wire, revealing an extra dimension. Another concept suggests that extra dimensions might be vast, but inaccessible to us. Our universe could be like a sheet of paper floating in a much larger space, with our everyday experiences confined to the surface of that sheet. We would be unaware of the space above or below us, just as a 2-dimensional being on a flat plane would be oblivious to the concept of height. Some theories propose that extra dimensions could be separated from our familiar 4-dimensional space-time by enormous amounts of energy. This would mean that under normal circumstances, matter and light would be unable to enter or interact with these hidden realms, making them effectively invisible to us. Lastly, these extra dimensions might manifest in ways we do not yet recognize. Our brains and sensory organs have evolved to perceive and interpret a four-dimensional universe. It is possible that evidence of extra dimensions surrounds us, but we lack the cognitive framework to process and understand this information, much like a colorblind person cannot distinguish certain hues that are obvious to others.
M-theory represents a groundbreaking advancement in theoretical physics. Building upon and unifying various versions of string theory, this comprehensive framework proposes that our universe consists of 11 dimensions, expanding beyond the 10 dimensions suggested by earlier string theories.
At its core, M-theory posits that the fundamental components of the universe are not point-like particles, but rather vibrating one-dimensional strings. These strings can oscillate in different ways, giving rise to the diverse particles and forces we observe in nature. M-theory takes this concept further by introducing two-dimensional membranes, or branes, which can exist in multiple dimensions. One of the most intriguing aspects of M-theory is its potential to reconcile quantum mechanics with general relativity, two pillars of modern physics that have long seemed incompatible. By providing a unified description of all fundamental forces and particles, M-theory offers a promising path toward a theory of everything, a long-sought goal in physics. While M-theory remains highly speculative and lacks experimental evidence, it continues to captivate physicists with its elegant mathematical structure and its potential to unlock the deepest mysteries of the cosmos. As scientists work to develop testable predictions from M-theory, it remains at the forefront of our quest to understand the fundamental nature of reality. The concept of extra dimensions could revolutionize our understanding of gravity. While we perceive and interact with three spatial dimensions and one dimension of time, some theories suggest our universe might contain additional hidden dimensions. These extra dimensions could explain why gravity appears weaker than other fundamental forces. In this scenario, gravity might not be inherently weaker, but rather spread out across these extra dimensions. This would mean that gravity is just as strong as other forces, but we only experience a fraction of its true strength in our observable four-dimensional space-time. The rest of its influence could be dispersed into these hidden dimensions, making it seem comparatively weak from our perspective. This idea ties into string theory, which proposes that the fundamental constituents of the universe are tiny vibrating strings of energy. These strings would require extra dimensions to vibrate in ways that could produce all the particles and forces we observe. If true, gravity could be unified with the other fundamental forces, solving a long-standing puzzle in physics. Understanding extra dimensions could also shed light on other cosmic mysteries. It might help explain dark matter, dark energy, or even the nature of black holes. By expanding our view of the universe beyond the dimensions we can directly observe, we might uncover new insights into the fundamental workings of reality itself. Scientists are employing various ingenious methods to search for evidence of extra dimensions beyond the four we experience in our everyday lives. One approach involves using powerful particle accelerators, like the Large Hadron Collider at CERN. By smashing particles together at incredibly high energies, researchers hope to create conditions where particles might momentarily escape into extra dimensions, leaving behind a telltale signature of missing energy in the detectors. Another experimental avenue explores the possibility that gravity might behave differently at very small scales due to the influence of extra dimensions. Scientists use extremely sensitive instruments to measure gravitational forces between objects separated by tiny distances, looking for deviations from the expected behavior of gravity in three spatial dimensions. Astronomers are also joining the hunt, searching the cosmos for signs of extra dimensions. They analyze the cosmic microwave background radiation, the afterglow of the Big Bang, for subtle patterns that could indicate the presence of additional spatial dimensions in the early universe. Some researchers even propose that certain properties of black holes or the expansion rate of the universe might be influenced by extra dimensions, prompting detailed observations of these phenomena.
These diverse experimental approaches demonstrate the creativity and determination of scientists in their quest to unravel the fundamental nature of our reality. While no conclusive evidence of extra dimensions has been found yet, these ongoing experiments continue to push the boundaries of our understanding and may one day reveal new aspects of the universe hidden from our everyday perception.
The discovery of extra dimensions would revolutionize our understanding of the cosmos and potentially redefine what we consider to be beyond our universe. These hidden dimensions, if proven to exist, could explain many mysteries in physics and open up new realms of possibility for the structure of reality.
Extra dimensions might provide a framework for parallel universes or alternate realities. They could exist alongside our familiar three spatial dimensions and one time dimension, but remain invisible to us in our everyday experience. These additional dimensions might be compactified, curled up so tightly that they are undetectable at the macroscopic scale, yet play a crucial role in the fundamental workings of the universe. The existence of extra dimensions could also shed light on the nature of dark matter and dark energy, two of the most perplexing aspects of modern cosmology. These elusive components might reside or interact primarily within these hidden dimensions, explaining their apparent invisibility in our observable universe. Furthermore, extra dimensions could potentially connect our universe to others, forming a vast multiverse. This concept challenges our notion of what lies beyond our cosmic horizon, suggesting that our universe might be just one of many interconnected realms, each with its own physical laws and properties.
The discovery of extra dimensions would thus expand our cosmic perspective, forcing us to reconsider the very nature of reality and our place within it. The concept of an edge to the universe is one of the most intriguing and challenging ideas in cosmology. Current scientific understanding suggests that the universe does not have a physical edge in the way we typically think of boundaries. Instead, the universe is believed to be infinite, or, if finite, to have a shape that wraps around itself.
Our observations indicate that the universe is expanding in all directions, with every point moving away from every other point. This expansion is not happening within some larger space, but is the stretching of space itself. As far as we can see in any direction, the universe appears to be uniform and follows the same physical laws.
If the universe is indeed infinite, the question of an edge becomes meaningless. An infinite universe would extend forever in all directions, without any boundary. On the other hand, if the universe is finite, it might be what scientists call positively curved, like the surface of a sphere. In this case, traveling in one direction would eventually bring you back to your starting point, similar to how circumnavigating the Earth works.
It is important to note that these ideas refer to the observable universe, which is limited by the distance light has traveled since the Big Bang. What lies beyond the observable universe remains a subject of theoretical speculation and ongoing research in cosmology. When scientists discuss the edge of the universe, they are not referring to a physical boundary in space. Instead, they are describing the farthest distances we can observe from Earth. This limit is called the observable universe, and it is determined by the speed of light and the age of the universe. Light from the most distant objects has taken nearly 14 billion years to reach us, traveling since shortly after the Big Bang. Beyond this cosmic horizon, we cannot see or detect anything because the light from those regions has not had enough time to reach Earth. This does not mean nothing exists beyond this point. It simply marks the current limit of our observations. The concept of an edge becomes even more complex when we consider the shape of the universe. Many scientists believe the universe might be infinite in size, or it could have a curved geometry that wraps around on itself, much like the surface of a sphere. In either case, there would be no true edge to space itself.
As our technology improves, and we develop more sophisticated ways of observing the cosmos, we may be able to push the boundaries of our observable universe further. However, due to the expansion of space itself, some regions will forever remain beyond our view, continuing to recede faster than the speed of light relative to our position.
The expanding universe presents a fascinating paradox when we consider its edge. In reality, the universe has no discernible edge in the way we typically think of boundaries. As the universe expands, it's not growing into some pre-existing space, but rather creating new space everywhere all the time. This expansion occurs uniformly throughout the cosmos, with every region of space stretching away from every other region.
Imagine a loaf of raisin bread rising in an oven. As the dough expands, each raisin moves away from every other raisin, but there's no center or edge to this expansion. Similarly, our universe's expansion doesn't have a center or an edge. From our vantage point on Earth, we observe distant galaxies moving away from us in all directions, but observers in those galaxies would see the same thing from their perspective. This uniform expansion is a fundamental property of space itself.
What we often refer to as the edge of the observable universe is actually the limit of what we can see due to the finite speed of light and the age of the universe. Beyond this cosmic horizon, the universe likely continues expanding just as it does in our observable region, stretching into distances we cannot yet fathom or observe.
The observable edge of our universe marks the limit of what we can see from Earth, but it doesn't necessarily represent the true extent of the cosmos. Beyond this boundary, the universe likely continues, possibly stretching infinitely. Current scientific theories suggest that the region beyond our observable universe might be remarkably similar to what we can see. It could contain countless more galaxies, stars, and planets, forming structures much like those we observe. This vast expanse might hold an unimaginable number of potentially habitable worlds, and perhaps even other forms of life.
However, some cosmologists propose more exotic possibilities. The concept of the multiverse suggests that our universe might be just one of many, each with its own set of physical laws and constants. These parallel universes could exist alongside ours, separated by higher dimensions we cannot directly perceive. Another intriguing idea is that the very nature of space, time, and matter might change beyond our cosmic horizon. Some theories predict that the fundamental forces governing our observable universe could behave differently in distant regions, leading to environments that defy our current understanding of physics.
Cosmological models offer varying perspectives on the universe's boundaries, each with intriguing implications. The most widely accepted model today, the lambda cold dark matter LCDM model, suggests that the observable universe is a tiny fraction of a much larger, possibly infinite cosmos. In this view, there is no edge or boundary to space itself, but rather a limit to how far we can see due to the finite speed of light and the age of the universe.
Some alternative models propose a finite universe with a specific shape, such as a three-dimensional sphere or a complex geometric structure like a dodecahedron. In these scenarios, if you were to travel in one direction long enough, you might eventually return to your starting point, similar to circumnavigating the Earth. Other theories, including some interpretations of string theory, suggest the existence of multiple universes or dimensions beyond our own. These models describe our universe as one of many bubbles in a vast multiverse, each with its own physical laws and properties.
Regardless of the model, a key point to remember is that when cosmologists talk about the edge of the universe, they often refer to the boundary of the observable universe, not necessarily a physical border of all that exists. This distinction highlights the ongoing quest to understand the true nature and extent of our cosmic home.
The cosmic web is the largest known structure in the universe, a vast network of interconnected filaments composed of dark matter and galaxies. This intricate pattern stretches across the cosmos, forming a framework that defines the large-scale structure of the universe. Imagine the cosmic web as an enormous three-dimensional spider web spanning billions of light-years. The filaments of this web are made up of dark matter, an invisible substance that interacts only through gravity. These dark matter strands act as cosmic highways, guiding the formation and movement of visible matter such as galaxies and galaxy clusters. At the intersections of these filaments, we find massive clusters of galaxies. These clusters are like cosmic metropolises, housing hundreds or thousands of galaxies bound together by gravity. Between these dense nodes are vast, nearly empty regions called voids, analogous to the spaces between the strands of a spider's web. The cosmic web plays a crucial role in the evolution of the universe. It influences how galaxies form, grow, and merge over cosmic time. By studying this grand structure, scientists gain insights into the distribution of matter in the universe and the fundamental forces that shape cosmic evolution.
Voids and filaments in the cosmic web offer crucial insights into the structure and boundaries of our universe. These vast cosmic features, spanning millions of light-years, reveal the intricate architecture of space on the largest scales we can observe. Cosmic voids are enormous, nearly empty regions of space that contain very few galaxies. They can stretch for hundreds of millions of light-years across, dwarfing even the largest galaxy clusters. Filaments, on the other hand, are the dense, thread-like structures that connect galaxy clusters and form the boundaries of cosmic voids.
Together, these elements create a cosmic web that resembles a colossal three-dimensional spider's web stretching across the observable universe. The distribution and characteristics of voids and filaments provide valuable information about the early universe and its evolution. They are thought to have originated from tiny fluctuations in the density of matter shortly after the Big Bang. Over billions of years, gravity caused matter to clump together, forming filaments and leaving behind vast empty space. Studying these structures helps cosmologists understand the limits of our universe in several ways. The size and number of voids and filaments give us clues about the total amount of matter in the universe and how it is distributed. This information, in turn, helps scientists refine their models of cosmic expansion and the nature of dark energy, the mysterious force driving the accelerating expansion of the universe. By mapping these immense structures, we gain a better understanding of the scale and composition of the cosmos, pushing the boundaries of our knowledge about the universe's ultimate limits. Dark matter exerts a profound influence on the structure and potential boundaries of the universe. Despite its mysterious nature, this invisible substance, which does not interact with light or other forms of electromagnetic radiation, accounts for approximately 85% of all matter in the cosmos. Its gravitational effects shape the distribution of visible matter, guiding the formation of galaxies and larger cosmic structures. On the grandest scales, dark matter forms an intricate cosmic web that spans the observable universe. This web consists of vast filaments and sheets of dark matter with dense clusters at their intersections. Ordinary matter, such as stars and galaxies, tends to collect within this framework, following the gravitational contours laid out by dark matter. This process has been ongoing since the early universe, with dark matter acting as a scaffolding for cosmic structure formation. The presence of dark matter also affects our understanding of the universe's potential boundaries. Its gravitational influence extends far beyond visible matter, creating enormous halos around galaxies and galaxy clusters. These halos stretch the gravitational reach of cosmic structures, blurring the lines between distinct systems and contributing to the interconnected nature of the cosmos.
Furthermore, dark matter plays a crucial role in ongoing debates about the universe's overall shape and whether it has definable boundaries. Its distribution and total quantity influence calculations of the universe's mass and energy content, which in turn affect models of cosmic expansion and the ultimate fate of the universe. As scientists continue to study dark matter, they hope to gain deeper insights into these fundamental questions about the nature and limits of our cosmic home.
The connection between cosmic inflation and the possibility of an infinite universe lies in the nature of this expansion. According to some models of inflation, the process may not have stopped everywhere at once. Instead, inflation might have ended in some regions while continuing in others, leading to the creation of multiple universes or regions of space-time that are causally disconnected from our own. This scenario, known as eternal inflation, proposes that new universes or bubble universes are constantly forming within an ever-expanding cosmic framework. If true, this would imply that our observable universe is just one finite region within a much larger, potentially infinite multiverse. However, it is important to note that while the theory of cosmic inflation is well supported by observational evidence, the concept of an infinite universe or multiverse remains speculative. The limits of our observable universe constrain our ability to directly test these ideas, leaving them as intriguing possibilities at the frontier of cosmological research. Cosmic inflation is a theory that describes the exponential expansion of the early universe in the first fraction of a second after the Big Bang. This rapid growth caused the universe to expand faster than the speed of light, stretching space itself to an enormous size in an incredibly brief moment. The concept of inflation helps explain several observed features of our universe, including its uniformity on large scales and the nearly flat geometry of space. It also provides a mechanism for the formation of cosmic structures like galaxies and galaxy clusters. Inflation's connection to the multiverse comes from the idea that the process might not have stopped everywhere at once. In some regions, inflation could have continued, creating new expanding bubbles of space-time. Each of these bubbles could potentially become a separate universe with its own physical laws and properties. This scenario, known as eternal inflation, suggests that our universe might be just one of many in a vast multiverse. Each universe in this multiverse would be causally disconnected from the others, existing as its own separate realm. While the multiverse concept remains speculative, it emerges naturally from some models of cosmic inflation, linking these two profound ideas in modern cosmology. Eternal inflation proposes a fascinating mechanism for the creation of multiple universes. This theory suggests that our universe began as a tiny region of space that underwent rapid expansion known as cosmic inflation. However, the key idea of eternal inflation is that this process never truly ends. As inflation continues, certain areas of space stop inflating and form bubble universes, much like our own. These bubbles contain regions where inflation has ceased, allowing matter and energy to coalesce into galaxies and stars. Meanwhile, the space between these bubbles continues to expand at an exponential rate, creating more room for additional bubble universes to form. This ongoing process leads to the creation of a vast multiverse, with new universes constantly emerging within the ever-expanding inflationary space. Each of these bubble universes may have its own unique set of physical laws and constants,
potentially differing from our own in significant ways. The eternal nature of this inflation means that the multiverse as a whole is endless, continuously giving birth to new universes across an infinite expanse of space and time. This concept challenges our understanding of the cosmos and opens up mind-boggling possibilities for the nature of reality beyond our observable universe.
The bubble universe model is a fascinating concept within inflationary theory that suggests our universe might be just one of many. This idea proposes that during the rapid expansion of the early universe, known as cosmic inflation, different regions of space stopped inflating at different times. These regions, where inflation ended, became separate universes, each with its own physical laws and properties. Imagine a vast, expanding sea of space-time foam. In this foam, bubbles form and grow rapidly. Each bubble represents a universe coming into existence, expanding at an incredible rate. Our universe would be one such bubble, but according to this model, there could be countless others. These bubble universes might have different fundamental constants, different types of matter, or even different dimensions. Some could be similar to ours, while others might be utterly alien and incomprehensible by our standards. The space between these bubbles continues to inflate, keeping them eternally separated.
This model offers a potential explanation for the fine-tuning of our universe. Instead of our universe being uniquely suited for life by chance or design, it suggests we simply exist in one of the countless bubbles where conditions happen to be right for our form of life to emerge. Other bubbles might harbor different forms of life or no life at all, depending on their particular properties. The concept of a multiverse suggests that our universe may be one of many, each potentially governed by its own set of physical laws. In different regions of the multiverse, fundamental constants and forces could vary, leading to dramatically different realities. For instance, in some universes, the strength of gravity might be much greater, causing matter to clump together more rapidly and form dense, short-lived worlds. In others, the electromagnetic force could be weaker, altering the behavior of atoms and the formation of complex molecules. The cosmological constant which influences the expansion rate of a universe might differ across the multiverse. Some universes could expand too quickly for stars and galaxies to form, while others might collapse back in on themselves before life has a chance to emerge. Even the number of dimensions could vary. While we experience 3 spatial dimensions and 1 of time, other universes might have additional dimensions, altering the very fabric of reality in ways we can scarcely imagine. These differences in physical laws would create a vast tapestry of diverse cosmic environments, each with its own unique properties and possibilities.
The landscape in string theory refers to the vast array of possible universes predicted by the theory. String theory, a candidate for a unified theory of physics, suggests that our universe is just one of an enormous number of potential universes, each with its own unique set of physical laws and constants. This landscape is incredibly diverse, containing an estimated 10 to the power of 500 distinct possible universes. Each of these universes represents a different solution to the equations of string theory, with varying physical properties such as the number of dimensions, the types of particles, and the strengths of fundamental forces. The concept of the landscape directly connects to the idea of the multiverse. In this context, the multiverse is the collection of all these possible universes predicted by string theory. Each universe within the multiverse occupies a different point in the landscape, with its own unique characteristics and laws of physics.
This vast landscape of possibilities raises intriguing questions about our own universe. It suggests that the specific properties of our universe, which allow for the existence of complex structures like galaxies, stars, and life, might be just one configuration among countless others. This perspective has profound implications for our understanding of the cosmos and our place within it, challenging us to consider why our universe has the particular characteristics it does among the multitude of possibilities in the string theory landscape.
The anthropic principle and multiverse theories intertwine in fascinating ways, offering potential explanations for our universe's seemingly perfect conditions for life. Multiverse theories propose the existence of numerous universes beyond our own, each with potentially different physical laws and constants. This vast array of universes provides a framework within which the anthropic principle becomes particularly relevant. The anthropic principle suggests that the observable properties of our universe must be compatible with the existence of conscious life that can observe it. In the context of multiverse theories, this principle takes on new significance. Among the countless universes that might exist, we inevitably find ourselves in one that allows for our existence. This does not mean our universe is special or designed for us, but rather that we could only exist in a universe with the right conditions.
Multiverse theories offer a potential solution to the fine-tuning problem, which questions why our universe appears so precisely calibrated for life. Instead of requiring a single universe to be inexplicably perfect, multiverse theories propose that out of an enormous number of universes, some will naturally have the right conditions for life. We simply happen to inhabit one of these life-friendly universes. This connection between the anthropic principle and multiverse theories shifts our perspective on cosmic coincidences. Rather than viewing our universe as uniquely designed, we can understand it as one of many possibilities where the conditions aligned just right for life to emerge and for us to ponder these very questions.
Inflationary multiverse theories have faced several significant criticisms from within the scientific community. One primary concern is the lack of direct observational evidence. Critics argue that since other universes are by definition outside our observable realm, these theories remain speculative and difficult to test empirically. Another criticism revolves around the concept of falsifiability. Some scientists contend that if a theory can explain any possible observation, it loses its predictive power and scientific value. This critique suggests that multiverse theories might be unfalsifiable, potentially placing them outside the realm of testable science. Critics also point out the potential for infinite regress in multiverse explanations. If our universe is part of a larger multiverse, what caused or created the multiverse itself? This leads to questions about the ultimate origin of existence, which some argue the multiverse concept does not adequately address. Lastly, there are concerns about the application of probability theory to multiverse scenarios. Some scientists question whether it is valid to apply probabilistic reasoning to the entire cosmos, especially when we only have one observable universe to study. This criticism challenges the statistical foundations upon which some multiverse arguments are built.
Testing predictions made by inflationary multiverse models present significant challenges due to the vast scales and energies involved. However, scientists have proposed several potential methods to gather evidence that could support or refute these theories. One approach involves searching for signatures of cosmic bubble collisions in the cosmic microwave background radiation. If our universe collided with another universe during its early expansion, it might have left subtle patterns in the temperature and polarization of this ancient light. Advanced telescopes and sophisticated data analysis techniques are being used to scour the cosmic microwave background for these telltale signs. Another avenue of investigation focuses on the distribution of matter in the observable universe. Inflationary multiverse models predict certain statistical patterns in how galaxies and other large structures are arranged. By mapping the cosmos in ever greater detail, astronomers hope to uncover evidence that aligns with these predictions. Gravitational waves offer yet another potential window into the multiverse. Some theories suggest that the collision of universes or the rapid expansion during inflation could produce distinctive gravitational wave signals. Future gravitational wave detectors,
both on Earth and in space, might be sensitive enough to detect these faint echoes from the birth of universe.
Brain cosmology is a fascinating concept in theoretical physics that expands our understanding of the universe beyond the traditional 4 dimensions of space and time. This theory proposes that our observable universe is actually a 3-dimensional membrane, called a brain, floating within a higher dimensional space known as the bulk. In this model, gravity is the only force that can move freely between different branes, while other fundamental forces, like electromagnetism, are confined to specific branes. This could explain why gravity appears much weaker than the other forces in our universe, as its effects might be spread across multiple dimensions.
Brain cosmology offers potential solutions to long-standing puzzles in physics, such as the hierarchy problem, which questions why gravity is so much weaker than the other fundamental forces. It also provides alternative explanations for the origin and evolution of our universe, suggesting that the Big Bang might have been caused by the collision of 2 branes. This theory opens up exciting possibilities for understanding parallel universes and the nature of dark matter and dark energy. While brain cosmology remains highly speculative and lacks experimental evidence, it continues to inspire physicists to explore new ways of thinking about the structure and origins of our universe.
Brain theory offers a radical reimagining of the universe's structure, expanding our cosmic perspective beyond the familiar 4 dimensions of space and time. This concept, rooted in string theory, proposes that our universe exists as a 3-dimensional membrane, or brain, floating within a higher dimensional space called the bulk. In this model, our universe is just one of many branes, each potentially harboring its own set of physical laws and fundamental forces. These branes might be stacked parallel to each other, separated by incredibly tiny distances in the extra dimensions we cannot directly perceive. The bulk itself could contain any number of dimensions beyond the 4 we experience. Gravity, unlike other fundamental forces, is theorized to operate across the entire bulk. This could explain why gravity appears so weak compared to other forces in our universe, as its effects might be spread across multiple dimensions.
Brain theory also suggests that the collision or interaction of branes could be responsible for cosmic events like the Big Bang. While brain theory remains highly speculative and lacks experimental evidence, it attempts to unify quantum mechanics and gravity, addressing fundamental questions about the nature of space, time, and the origins of our universe. It challenges us to consider that what we perceive as reality might be just a slice of a much grander multidimensional cosmos. In brain cosmology, the bulk refers to a higher dimensional space that encompasses our familiar 4-dimensional universe. This concept emerges from string theory and M theory, which propose that our universe might be a 3-dimensional membrane or brain floating within a larger multidimensional space. The bulk is often visualized as a vast, empty expanse that extends beyond the confines of our observable universe. It serves as the backdrop against which our universe, and potentially other universes, exist. This higher dimensional space is thought to have at least one more spatial dimension than our own universe, allowing for the possibility of parallel universe or other exotic phenomena. One of the intriguing aspects of the bulk is its potential to solve certain cosmological puzzles. For instance, it might explain the weakness of gravity compared to other fundamental forces, as gravity could be leaking into the bulk. Additionally, the existence of the bulk could account for dark matter and dark energy, as these mysterious components might be manifestations of how our brain interacts with the higher dimensional space. While the concept of the bulk remains largely theoretical, it has sparked numerous research avenues in theoretical physics and cosmology. Scientists continue to explore ways to test these ideas and search for observable consequences of living in a universe that might be just one part of a much larger multidimensional reality.
Brain collisions represent a fascinating concept in theoretical physics, offering a potential explanation for the creation of new universes. In this model, Our universe exists as a three-dimensional membrane or brane floating in a higher dimensional space. Other branes may exist in this same space, and occasionally these branes might collide with one another. When two branes collide, the enormous energy released could spark the formation of a new universe. This process is somewhat analogous to the Big Bang theory, but instead of emerging from a singularity, the new universe would be born from the interaction between two existing cosmic structures. The collision would release an immense amount of energy, potentially creating matter, space, and time as we know them. This idea stems from string theory and M theory, which propose the existence of extra dimensions beyond the four we can observe. These theories suggest that gravity, unlike other fundamental forces, can leak between branes, explaining why gravity appears weaker than the other forces in our universe. While brane collisions remain a highly speculative concept, they offer an intriguing alternative to traditional cosmological models. If true, this would imply that our universe might be just one of many in a vast multiverse, each created by cosmic collisions on an unimaginable scale. However, detecting evidence of other branes or collisions remains a significant challenge for modern physics.
The episodic universe model offers an alternative explanation for the origin and evolution of our cosmos. This theory proposes that our universe began not with a sudden expansion or Big Bang, but through the collision of two vast, flat membranes or branes in a higher dimensional space. In this scenario, these branes exist in a realm with more dimensions than the three spatial dimensions we observe. They move through this higher dimensional space, occasionally colliding with each other. The energy released during one of these collisions is believed to have sparked the creation of our universe.
Brane cosmology, which forms the foundation for the episodic model, suggests that our entire universe exists on a three-dimensional membrane within a higher dimensional bulk space. This concept stems from string theory, which posits that the fundamental constituents of the universe are tiny vibrating strings of energy. The episodic model attempts to address some of the challenges faced by the traditional Big Bang theory. It offers explanations for the uniformity of the cosmic microwave background radiation and the flatness of space, without requiring a period of rapid inflation. Instead, it proposes that these features arose from the nature of the brane collision and the subsequent evolution of the universe.
Brane cosmology offers an intriguing approach to addressing the hierarchy problem in physics, which puzzles scientists due to the vast difference between the strength of gravity and the other fundamental forces. This theory proposes that our universe exists on a three-dimensional membrane or brane floating within a higher dimensional space called the bulk. In this model, gravity is not confined to our brane but can spread out into the extra dimensions of the bulk. This spreading out or dilution of gravity could explain why it appears so weak in our three-dimensional world compared to the other forces. The other fundamental forces, in contrast, are thought to be confined to our brane, maintaining their full strength. The existence of extra dimensions in brane cosmology also suggests that the true scale of gravity might be much closer to that of the other forces than we observe. The apparent weakness of gravity in our world could be an illusion caused by its dispersion across these hidden dimensions. This concept provides a potential solution to the hierarchy problem without requiring the introduction of new particles or forces in our observable universe.
Brane cosmology not only addresses the hierarchy problem, but also opens up new avenues for understanding other cosmological mysteries, such as the nature of dark matter and dark energy. While this theory remains speculative and requires further evidence, it represents an innovative attempt to unify our understanding of the fundamental forces that shape our universe. Brane cosmology theories propose that our universe exists on a multi-dimensional membrane or brane within a higher dimensional space. While these theories remain speculative, scientists have considered several potential observational signatures that could provide evidence for their validity. One intriguing possibility is the detection of gravitational waves with unexpected frequencies or amplitudes. According to brane theories, gravity might be able to propagate through extra dimensions, potentially leading to gravitational wave signals that deviate from the predictions of standard general relativity. Advanced gravitational wave detectors could potentially pick up these anomalous signals, offering a window into higher dimensions.
Another avenue of investigation involves searching for slight variations in the strength of gravity over very large distances. Some brain models predict that the force of gravity might behave differently on cosmic scales compared to what we observe in our local environment. Precise measurements of galactic motions and the expansion of the universe could reveal these subtle deviations, providing support for brain cosmology.
Cosmic microwave background radiation, the afterglow of the Big Bang, might also hold clues. Brain theories suggest that our universe could have collided with other brains in the past, potentially leaving observable imprints on this primordial radiation. Detailed analysis of the cosmic microwave background could uncover patterns or anomalies that align with predictions from brain cosmology, offering tantalizing evidence for these multidimensional models.
Brain cosmology presents a radical departure from traditional Big Bang theory, offering a new perspective on the origin and structure of our universe. In this model, our universe exists as a three-dimensional membrane or brain floating within a higher dimensional space called the bulk. This contrasts sharply with the standard Big Bang model, which describes our universe as a singular four-dimensional space-time continuum. The key difference lies in how these models explain the beginning of the universe.